In the introduction video, we saw a 1,000-foot overview of the theory of incomplete measurements, a proposal to unify the theory of general relativity and quantum mechanics. In particular, we saw that the theory could be summarized in 5 key points. In this video, we will focus on the first point, namely that physics is all about measurements. All we know about the universe around us, we actually learn from measurements. Our own senses, our eyes, our hearing, our touch, our smell, our taste are all forms of biological measurement that give us information about the world. Physics is no different. Any data in physics, anything we put in equations, in charts, in diagrams or in plots, all that first comes from some kind of measurement. In the lab, we use sophisticated instruments, designed to provide precise, numerical results, like a voltmeter or a laser distance sensor. In everyday life, however, we often use simpler methods, like counting footsteps or visually checking the weather. There are also devices, like fire alarms or thermostats, that effectively measure something such as the presence of smoke or a temperature, but do not produce a numerical value. A fire alarm, for example, will inform you using a loud siren or a flashing light. But what are these measurements we keep talking about? Let us attempt to define them. The theory presented here defines a physical measurement using the following 6 simple postulates. First, a measurement is a physical process. Second, that process connects an input and an output chosen ahead of time. Third, a measurement can be repeated. Fourth, it gives information only about its input. Fifth, the information is given through a manifest physical change in the output. Sixth, the output change can be given a symbolic interpretation. We can make 2 important observations here. On one hand, there are physical processes that are measurements, like a voltmeter, or a measuring tape, or a fire alarm. On the other hand, not all physical processes are measurements. For example, rolling a dice does not give information about the position of your hand or the temperature of the room or anything else. So it satisfies all the postulates, except the 4th one. It is not a measurement. What these 2 observations teach us is that measurements are a choice. We choose, among all physical processes, those that work well as measurements. Let's discuss these 6 postulates a bit more. The first postulate tells us that a measurement is just a regular physical process. There is no magic involved. There is no need to invoke any special properties of an observer, for example. There is no need to invoke some mystical property of consciousness either. The measurement happens entirely within the universe. You don't need to exit the matrix to measure something. The second postulate tells us that your voltmeter must measure the difference in electrical potential between its 2 probes, not some other place in the room. This is one of the reasons the probes are so well insulated, the other being your safety, of course. It also tells us that the voltmeter's needle should move in a way that directly relates to the voltage. The third postulate tells us that if you just measured 220 volts and double-check, you expect about 220 volts again, not some other random value. You can also repeat in space. For example, in a digital camera, the same sensor is repeated literally millions of times. If your camera has 20 megapixels, it means that the exact same light measurements are repeated about 60 million times, 20 million times for each of the 3 primary colors. The fourth postulate tells us that a measurement is focusing on its input. Your voltmeter should give you information only about the electrical potential between its probes, not about the temperature of the room, your age or the length of the wall. The voltmeter should be as insensitive to all these other quantities as possible, and it's a good thing. Symmetrically, the fifth postulate tells us that we know about what the voltmeter measures by observing its output. In that case, the manifest change is some visible screen change. If you can't read the screen, the voltmeter is broken and is no longer a valid measurement device. The manifest physical change does not need to be visible. In the case of a fire alarm, it may be a rather loud audible sound. In the case of a digital sensor, it can be some numerical data sent over the internet. In the case of our own biological senses, it is a change in nerve potential. The sixth postulate tells us that the manifest change does not mean anything by itself. If you hear a loud siren, you cannot interpret what it means without knowing what the alarm is supposed to detect. If the needle of your voltmeter moves, you can't tell the voltage without knowing the range. Counting the tick marks on a pocket ruler does not mean anything by itself if you don't know whether the ruler measures inches or centimeters. So as you can see, these postulates are nothing mysterious. If you are familiar with the postulates of quantum mechanics, you may notice that this is much simpler. The theory of incomplete measurements is rooted in good old-fashioned common sense. Yet there are similarities. For example, the third postulate ensures consistency of the observations, and plays the same role as the collapse of the wave function in quantum mechanics. We will compare the two sets of postulates in another video. For now, let's explain why this theory refers to incomplete measurements. What do we mean by incomplete? The definition of physical measurements we just gave does not state that measurements tell us everything there is to know. Quite to the contrary, the expectation is that any given measurement only provides a very partial and limited view of reality. For example, a voltmeter tells us very little about the temperature of its object. That is by design. That is a good thing. Conversely, a thermometer does not normally depend on the voltage in your home's electrical circuitry. Of course, this may not be entirely true. A voltmeter, for example, may detect very high temperatures. That melted plastic smell gives it away. Conversely, if you use a thermometer, it may be sensitive to the fact that a big electrical surge caused a fire. These exceptions only prove the point actually. A measurement device is never perfect. Measurements can contain errors. They can take time. If you count how many people there are in your city all by yourself, it can legitimately be called a measurement. However, it will remain incomplete for a very long time. The quality of that measurement will improve over time. First, you count yourself and you know that the number is at least 1. Then you count your family members, and so on. So what we learn from a measurement process may evolve over time. By the way, the theory presented here would consider this as the slowly observable collapse of a wave function, in case you were wondering. Similarly, any measurement device may gradually turn from a good measurement device to a bad one based on various external factors. A good theory of physics should be able to deal with such cases, and the theory of incomplete measurements is arguably the first one that does. We will see in another video how this leads to a new principle of relativity. More importantly, in this new approach of the laws of physics, observations simply tell us something about the universe, they are not the universe. The symbolic result of a measurement is only information. It is a view of reality, it is not reality itself. This eliminates a large fraction of the big philosophical issues which are commonplace with quantum mechanics. In the next video, we will see that what we just said has consequences. Specifically, that the space-time continuum does not really exist, first because there is no continuum, second because there is no space and no time.